Okay, this is the level 0 bootloader. So it will copy the code that you upload over the UART into the memory, the start of RAM, at address 300 in hex. Once all the code has been uploaded over the UART, it will then branch to it. It actually has a checksum as well, so as it's coming in over the UART, it will compute the checksum, and if that matches the checksum at the end of the UART image, then it will branch to the start of the code, and if not, then it will just reboot and wait again for the code. So if we look at the console here, this is coming in through the FTDI UART just here. So this is it, it's just waiting for some hex from the UART. Now, the operating system I've built here, which I assembled with my assembler, the very start of the operating system is looks like this. It's going to be, so here it is, F main. It's one of the F main. There we go. So T32 is the extension for my assembly code. F main means functional. Yeah, the F prefix means functional, and the D prefix means data. So, for example, this is all the data associated with main, and this is the code in main. So this is the start of the OS here. So at the very beginning, you clear all of the interrupt control flags in the CSR by setting the read modify write bits to 1-1, and that's it. And that will write zeros everywhere else in that field, in the interrupt field. Then you just set the stack pointer to the kernel stack base, which is a label somewhere up here. There we go. And then you set the ISTP register to the interrupt service table pointer, which is here. So software interrupts are below the label, hardware interrupts are above the label. So calling a software interrupt with, so executing the SWI instruction with a positive number will call one of these with it, so because it's got a positive offset from the interrupt service table label. Hardware interrupt will automatically, depending on which pin it comes in, generate an offset of -4, -8, -12 or -16, and that will execute one of these. Now the scheduler, which is responsible for the multi-threading of the OS, is executed. That's on the lowest priority interrupt pin, which is pin 3. So highest priority is 0, which at the moment doesn't do anything. Second highest is 1, which is the timer's ISR. That just runs a timer which counts once a second on this hex display. And then nothing on 3, and then the scheduler is on 4, and that's called once every, I don't know, a few milliseconds or something. I can't remember what the interval is. It's all set up in main. So here we go. Yeah. So the first thing we do here is we configure the UART. So my OS doesn't do automatic UART device enumeration yet. It does do automatic SPI device enumeration, but not UART yet. So it just clears the GPIO LEDs, whatever. Prints the welcome message, which you'll see in a minute when we boot. It then initializes the memory management unit, which is how I've implemented malloc and free in a very sort of simple way, which I'll explain later. But it works. Works quite well actually. Then I initialize some timers. So this is like, you know, if a program wants a timer, there's like a timers module as well. Then I init multi-threading, and in this function, for example, the scheduler will be tied, I can't remember actually. Anyway, multi-threading is initialized here, and the main rejoin point is passed as well, so that when scheduling is completed, if there are no more threads left, if you kill every single thread, then the scheduler will auto-exit and rejoin the point that was passed in R0, register 0, to the threads in it function. And then here we just print some information. Then we register some threads, which is quite clunky at the moment. I haven't wrapped it up in a function yet. Then we enumerate the SPI devices. And then what we do is we start creating SD contexts on SPI devices which have SD cards attached to them. And that information is actually read from the sort of the header at the base of the peripheral address. So an SPI device has got a particular identifier, but an SPI SD device has got a different identifier. So it'll enumerate them all as SPI devices, but then the SD driver will then go and create SD contexts on top of SD capable SPI devices. And then down here we init the tick, so this is what's tied to the scheduler. Then we save the kernel stack pointer. Then we just print a handover message, we enable interrupts, and we just enter an infinite loop here waiting for the scheduler to take over. And this is where the rejoin point of main would be. Okay. Now, although there are a large number of files here that the OS is composed of, and this isn't by any means all of them, all that happens is what the assembler does is it essentially concatenates all of them in a very specific order that I've chosen, and it just assembles it as one large file. So the only reason I've split it up into different files here is just because it's much easier. It's much easier to work with. And then, but actually, as one big file, it's basically it's about 2,700 lines of assembler now. It's getting quite big. So when you build the OS using the assembler that I wrote in C, using Flex and Bison, if we build that, this is what the make file does. It just assembles all of the files in this order. So hkernel is the kernel header, which basically contains information that about various functions and software interrupt numbers. So if you want to write an application to run under the Snow OS, so I've called it Snow, this operating system, then you include hkernel in your assembly program, and that will define certain labels for you, like various SWI labels. So you can use SWI malloc and SWI threads create and stuff like that. Right, so that will produce a UHI file, which is a UART hex image, which is here. We've just rebuilt it, so it'll ask me if I want to reload it. I use TextPad because it's brilliant. Now, how does the bootloader know what the start and end of an image is? Well, it's easy. The only non-alphanumeric character that will turn up in an image is the asterisk, and there is one at the very beginning of the image, and there is another one at the very end of the image, just after the checksum. As soon as it sees the last one, it knows that it's seen all of the code. And I think the checksum works such that if the entire image is summed to 0 in 32-bit chunks, then it is assumed to have been uploaded correctly. Now, you have to forgive me for forgetting certain things about this, because it's been quite a few months of work every so often when I've had some spare time at home alone. so I can't remember everything in a lot of detail, but I am currently in the process of writing some documentation to help me remember, because every so often when I come back to it I have to sort of look through all of the code and try and work out what exactly I did last time, and then I add more comments if it wasn't immediately clear when coming back to it. Commenting is key, that's for sure. So let's select and copy all of this, and then right click it into putty. Here we go. Level 0 bootloader is receiving it. Copied it to RAM, let's branch to the code, and now the kernel has booted, and you can see this little terminal just there. So if you type top here, this will tell you that there are 4 threads currently in flight. The performance counter, which frankly doesn't really do anything at the moment. The terminal thread, which is what you're looking at, and 2 SD daemons, and that is because there are 2 SD card devices. One on my little daughter board, and one on the DE1 board itself. So, first thing we've got here is the build stamp and my name. Then we've got the first thing it does is calculates the RAM size, and it initializes the memory management unit. I call it the M pool because it's all I could really think of naming it sensibly. I mean, it's not a heap, it's just, you know, some arbitrary thing that I came up with. It's just a pool of memory, so I just call it a pool. Now dynamic memory allocation is available, so I just print out all this information so that it helps me work out what's gone wrong if something hasn't worked properly during boot. Then multi-threading is initialized but not started. Then it registers certain threads, and these are the handles returned from SWI threads create. And the terminal thread. Then it enumerates the SPI devices. And you get certain handles from the enumeration. And then you create SD contexts on SPI devices which have SD cards attached to them, or SD card cages. It's found 2 of those out of the 3, because the third one is this little SPI device here, which eventually the level 1 bootloader will go on, and the level 0 bootloader will first check for an image in that. Then it starts multi-threading. It just hands over to the scheduler and waits, and then this is the terminal thread starting up. Now you can upload other UHIs into the terminal, and you can run them in the foreground or the background, and it'll create a new thread running that task if you choose to run it in the background. These are the threads currently in flight, I've already said that, and those are their handles. You can also say my handle, and it'll tell you the handle of the caller, which in this case is the terminal. As you can see, 4100 is the terminal's handle from top above. Let's see what else we can do. So you can dump the contents of memory as well. So if we do an mdump of, let's go for 40FC, which is the handle of the first thread there. 40FC. That's at the top here. Now this table, which is full of Fs, is the thread handle table. So if there's a non-all Fs value in this table here, then the scheduler knows that this is a thread that's currently in flight. So every time it's interrupted, it will move to the next valid entry of this table until it gets all the way to the end, and once it gets to the end, it'll then wrap to the beginning again. And each one of these numbers here is a pointer to the thread's info struct. So that's just a little data structure which contains pieces of information like the stack pointer, a pointer to the name of the thread, and just, you know, other bits and pieces like that, which again I can't remember offhand. I'd have to look in the code. And here you can kill a certain task as well. You cannot kill yourself. So if you try and type kill and then the terminal's handle into the terminal, it'll fail. But you can kill any of the others. You can kill the performance counter. In fact, let's do that. Let's kill the performance counter. It's completely useless after all. So 40FC. So let's type kill and then 40FC. Great. So that's been destroyed, and oh yes, and of course another thing the thread info struct pointer points to, sorry, or the thread info struct contains is information about memory that has been allocated to that thread. So when you destroy a thread, you can free it. So if we then do an mdump of the 40FC again, you should see the first entry in this table has gone to all Fs. 40FC. There it is. That thread is no longer in flight. So only these three are running. And if you do a top, you can verify that that is indeed the case. You've got the terminal and the two SD daemons. So now, one of the things the SD daemon does is it keeps trying to talk to the SD card periodically using one of the timers that the OS provides. And if it can't talk to it, then it assumes it's been unplugged, and then it will constantly try and initialize it. And then once it successfully initializes it, if someone happens to plug one in at some time, it will then report, it'll set a flag in the driver, that instance of the driver, saying, yes, this SD card is now available. And it also lights up these LEDs here, the two middle ones. And if you pull it out and it can't talk to it, it clears them as well. So you'll see that. So if I undo that, then it's just realized it's disappeared. It's printed SD card removed on the console. And then if I plug the SD card back in, there you go, it's now found it again. But nothing else is printed here. So that's it really. If we reboot, all it does is it goes back to where we started, where we then get a chance to upload the code again. And this counter stops here. So this counter, which I don't think I've shown you, it is the thing that the other ISR is connected to. Literally once a second it'll just increment the hex value on this 4-digit hex display. And now obviously, because it's rebooted, you can see that the kernel's not running anymore, and so you can pull out the SD card, you can plug it back in, the lights won't change, this counter won't keep counting. If we upload the kernel again by just pasting it in, the other thing the level 0 bootloader does is it actually puts the numbers that are coming in on those LEDs, which is why they were flashing. And there you can see there's the counter going, and there we are, we've booted again. Yeah. Right, well that's it really. I hope you enjoyed it, and once I have finished writing my FAT32 file driver, which is next, I will hopefully be able to actually make this thing file system aware and get files from and write files to the SD card. But until next time, thanks for watching. And if you have any questions, just shove it on the post.